Hey everybody. Today we're talking about alternating series and the alternating series test. An alternating series is just one where the adjacent terms have opposite signs. So the terms go positive, negative, and so on. A few quick examples: 1 minus a half plus 2/3, and so on. 2 minus 4 plus 8, and so on. Negative a third plus a fifth minus a seventh, and so on. Sine pi over 2 plus sine 3 pi over 2 plus sine 5 pi over 2, and so on. This last one doesn't at first glance look like an alternating series, but it is nonetheless, despite all those plus signs in between. Because sine of 3 pi over 2 is negative, the sine of 7 pi over 2 is negative, and so on. The most frequent form that you'll see for alternating series are sigma negative 1 to the k a sub k, or sigma negative 1 to the k plus 1 a sub k, where a sub k is always going to be positive. The alternating series test is a very simple way to determine whether an alternating series converges or not. So suppose we have one written in this more standard form, sum negative 1 to the k a sub k. You want to check two things. Is that sequence a sub k non-increasing? In other words, does it ever get bigger? And is its limit 0? If both of those things are true, then the series converges. This is a very simple test because it lets you look at the sequence a sub k rather than the series sum negative 1 to the k a sub k. It's a lot easier to determine convergence and divergence of sequences than series. Let's do 3 examples just to get a feel for how this works in practice. The first example, sum negative 1 to the k minus 1, 1 over k, is the alternating harmonic series. So remember, the harmonic series is 1 plus a half plus a third plus a fourth. Here we've just thrown in the negative 1 to the k minus 1. We're checking three different things. First of all, is the series alternating? Yes, that's clear because of the negative 1 to the k minus 1. Second of all, does the general term go to 0? Is the limit as k goes to infinity of 1 over k 0? Yes, of course it is. The denominator is getting larger, the numerator's not, the whole thing goes to 0. Finally, is the general term decreasing? In other words, is 1 over k decreasing? The answer is yes. As k gets larger, the whole thing gets smaller. Therefore, the alternating series test applies. The alternating harmonic series is convergent. Remember, by the way, that the harmonic series without the pluses and minuses diverges. So that's an important distinction to see. Problem 2. Sum n equals 2 to infinity, negative 1 to the n squared over n squared minus 1. As always, when we're thinking about convergence and divergence of infinite series, the starting point doesn't matter. So it doesn't matter whether we start at n equals 1, 2, or 10, or a million. Here, we've wanted to leave out 1 so that we don't get a 0 in the denominator ever. We need to check 3 things, of course. Is it alternating, decreasing, and does the general term go to 0? The first one's obvious. It's clearly alternating because of the negative 1 to the n. Does the general term go to 0? And is the general term decreasing? In order to check those 2 things, we'll consider the corresponding function for n squared over n squared minus 1. F of x equals x squared over x squared minus 1. Basically, just taking the formula for the general term, putting in x's for the n's, and viewing it as a continuous function. So, first of all, let's check to see if it's decreasing. We do that with the derivative. We do a quotient rule, low d high minus high d low, draw the line, square below. Do a little bit of simplification, and remembering that x is always going to be positive, because n is starting at 2 here, we get that this is always going to be negative. So that function f of x is in fact decreasing. Next, we need to check that the general term goes to 0. We want to take the limit as n goes to infinity of f of x squared over x squared minus 1. We do L'Hopital's rule, for example, because this is an infinity over infinity form, 2x over 2x, and the 2x's cancel. We're looking at the limit as x goes to infinity of 1, also known as 1. So here, the general term of the series is not going to 0. an is not going to 0. So this series must diverge. Problem 3. Sum n equals 0 to infinity, negative 1 to the n squared over e to the negative n. So this is going to be an alternating series. N squared e to the negative n is always positive. So we need to consider whether it's decreasing, and then we need to look at its limit. Again, we'll look at the corresponding continuous function f of x equals x squared over e to the negative x, and take a derivative to check to see if it's decreasing. This time it's a product rule, 2x e to the negative x minus x squared e to the negative x. Factor out x and factor out e to the negative x, you're left with 2 minus x. So when x is greater than 2, for example, we see that this is going to be negative. So it's okay that it's increasing at first. It's decreasing after x equals 2, after n equals 2. So that's enough for us. Now we need to take a limit. We need to make sure that the general term of the series is going to 0. We want the limit as x goes to infinity of x squared e to the negative x. This is going to be an infinity times 0 indeterminate form. So we want to rewrite it as an infinity over infinity form, putting the e to the negative x in the denominator and making that exponent positive. Now we can use L'Hopital's rule, 2x over e to the x. Getting infinity over infinity again, we use L'Hopital's rule a second time, 2 over e to the x. Now as x goes to infinity, the denominator is going to infinity, the whole fraction is going to 0. So this series overall is alternating, decreasing, and has a general term going to 0. So it must converge.